You have the two bucket B1 and bucket B2. So in the bucket B1 you have the three blue balls, three yellow balls. Here you have the two blue and four yellow. Now the question is that if we randomly draw a blue ball, what is the probability of being in the first bucket? Means what you need to determine? You need to determine that the probability for the B1 given the blue ball, and blue ball you can represent with the event like A. So A denotes the selecting the blue ball. Blue ball. So this actually we are interested to know this. If we randomly draw a blue ball, what is the probability of being in the first bucket? So what is the probability that blue ball is coming from the first bucket? And bucket B1 and B2, here we have to assume that both are the equally likely. Means you can also take the blue ball from the B1, bucket B1, or you can also take the ball from the bucket B2. So both having the equally likely probability means what you have? Probability for the B1 and probability for the B2 is what? 0.5. So you have the probability of B1 and probability of B2 is 0.5. This is the sample space, and your sample space has two events, and your sample space total outcome in your sample space is what? In your sample space you have the 12 balls. Out of the 12 balls you have the 5 balls which are blue, and you have the 7 balls which are the yellow. So your sample space is partitioned into two different set. One is you can say in the form of the bucket B1 and B2, and the answer is 3 by 5. How can you solve? What you need for solving this? Okay. So A is the event for selecting a blue ball. So this is no, and we are interested for determining the probability for B1, and this is the. So this is actually the question we have to answer. With the help of the Bayes theorem, you can write probability of B1 given A can be written as probability of B1 and A divided by probability of A. This you can say that probability of B1 times probability of A given B1. So B1 occurred, and you need to compute the probability for A given B. And then you have the probability for A. You know the probability for B1 and probability for A given B1. So what is the probability for B1? Probability for B1 is equal to 0.5. We assume that both are equally likely. Probability for B2 is also 0.5. Both are equally likely. And what is the probability for like A? Probability for A given B1. What is the answer for this case? If you are asking that what is the probability that the ball is blue, and given that it is coming from the basket B1. So now this is the sample space you have. So what is this? How many blue balls are there? 3, and 3 yellow balls. So what is the probability for the blue balls given that it is the bucket 1? So this is the 3 by 6. So this is 3 by 6. And what is the answer? Again, this is the 0.5. Okay. 0.5, or you can write in the fraction also. There is no 1 by 2 you can also write if you want to compute easily. Similarly, you can compute probability of A given B2. So A given B2. So what is the probability for the blue balls given that bucket is B2? So how many blue balls are there? There are 2 blue balls and 4 yellow balls. You have the 6. Total balls are 6. 2 blue balls. So 2 by 6, and this is actually 1 by 3. Now we have got this thing. So we know the probability of B1, we know the probability of B2, we know the probability of A given B1, we know the probability of A given B2. Now, so you know B1, probability of B1, you know probability of A given B1. Now you need to know probability of probability of A, and probability of selecting a blue balls. Now the blue balls is not, you are not specifying the B1 or B2. This is for the whole. This is for the whole sample space. This is the sample space. This is the sample space here, and this is the partition. So again, probability for the A is what? Probability of B1 and A plus probability of B2 and A. Okay, because you have the two partitions only. So what is the probability for B1 and A? How you can write? This is probability of B1 multiplied by probability of A given B1 plus probability of B2, okay, and multiply by probability of what? A given B2. So probability of B1 is what? 0.5 means 1 by 2. Probability of A given B1, again 1 by 2 plus probability of B2 is again 1 by 2, and probability of A given B2, is what? 1 by 3. What is this? This can be written as 1 by 4 plus 1 by, and this is 5 by 12. So this is 5 by 12. Probability for B1 given A can be written as, you have, like this, probability of B1. So what is the probability of B1? This is 1 by 2 multiply by probability of A given B1. Is again 1 by 2 divided by 5 by 12, and this is what? 1 by 5 multiply by 12 by 4, and this is the answer. So this is the answer. So this is the use of your Bayes theorem. Now you can solve this problem. This is somewhat tricky. A laboratory blood test is 95% effective in detecting a certain disease when it is in fact present. So when the disease is present and you are going to go for the blood test, then there is a 95% effective. However, the test also yields a false positive. False positive, false positive means just like a healthy person is tested. Some healthy person is going to test it, and your result says that positive. So this is the false positive. Means actually the person is not suffering from any disease, but your test result is positive. So that's why this is the false positive. And this false positive result is 1%. So you can come to know that blood test is, if you go for the blood test, then it is the 95% effective when the disease is there, and when the healthy person is tested, then it gives the false positive as 1%. Okay, so this we know only. If a healthy person is tested, then with the probability 0.01, the test result will imply he or she has the disease. Now the question is that 5% of the population, means in your sample space, you have the sample space, and 5% of the population in your sample space actually has the disease. This says, then we are going to compute what is the probability a person has the disease given that the test result is positive. And you know that test result is positive in two different cases: when the person has actual disease, or it may be the false positive. Okay, so if somebody says that okay, the test report is positive, then you need to know that what is the probability a person has the disease. Because sometimes healthy persons also comes positive. So this is actually we need to. and say that only 0.5% of the population actually has the disease, and the false positive cases are just 0.01. This is the 0.01. So how you can compute this? So what is the probability a person has disease given that the test result is positive? If you disease, you can assume that disease for the D event, that the person is having the disease, and with some different letter like E, you can say that the test result is positive. So you need to compute the probability like this. So D be the event that the tested person has the disease. You are testing a person and person has the disease. We are denoting by the D. E be the event that the test result is positive. Now the test result is positive. This is the only. So person may be healthy and your test result may be positive. Person may not be healthy and your test result is positive. So we are given that we need to know actually this. What is the probability that the person is having the disease given that the test result is positive? Because we know that test result is positive in two different scenarios. Actually, if there is a disease, or it may be the case of the false positive. So that's why you need to know the probability of this. Probability for the event that person has actually the disease given that the test result is positive. And now you can compute like this. Okay, that this is the Bayes theorem. The answer is this. How you can compute this? So we are interested in this. We are interested to determine the probability that person has actually disease given that the test result is positive. DE means this is the joint probability, you can say. This means P, D and E divided by probability for the E. This. And this is the probability for D given A. We are interested. Now here you have the sample space. So here you have, okay, this is the sample space, and what it says that it is the two partition. There are two this is the sample space consists of what? Sample space consists of the population. So you have the population. Okay. So this is the population. And this sample space consists, this is the total population you have. You have the total population. And question says that 0.5% of the population actually has the disease. So here there are two partitions, out of which 0.5% of the population actually has the disease. 0.5 means you can say that this is one partition and this is other partition. And what is the population for which you don't healthy population? What is the healthy population? 99.5%. And here you have the 0.5%. So you have the two partition. So one is of the disease, having the disease, and other having the no disease, actually healthy person, no disease. Now what we are going to compute? We are going to compute, we need to know that if the test result is positive. Now test result can be positive if the person is having the actual disease also, and test result can also be positive when person is not having the disease. So in this case also test result can be positive. In this case also test result can be positive. So actually we need to know that if we have the test result positive, what is the probability that actually we have the disease? This is actually we are interested. So we can compute like this. So this can be given as probability of D times probability of E given D divided by probability of E. Now probability of D is probability of D multiplied by probability of E given D. This means what is the probability that the test result is positive given that the person has having the disease? What is the probability? A laboratory blood test is 95% effective in detecting certain disease when it is in fact present. So this is the case. So when disease is present, did represent that when disease is present. So this says that what is the probability that the test result is positive, given that the person has actually the disease. So 95%. So you know this probability. You know the probability for the disease means how, what is the probability for the disease, how many in population, how many people are having actually disease, 0.5%. So we also know this, but we don't know the probability of E, positiveness, because test result can be positive here also, test result can be positive here also. Now this you can determine. So probability for the test result is positive can be given as joint probability. So probability of disease and test result is positive, plus probability of D complement, actually person is not having this disease. So probability of D complement means person is healthy, and person is healthy and you have the test result is positive. This. Now how you can compute? So you can compute as probability of D times probability of D, probability of E given D. So probability of E given D plus probability of D complement multiplied by probability of E given D complement. This actually, and you can substitute here. You will get. So you can compute here. What is the probability of D? 0.5%. Once this you can say multiply by probability of E given D. What is this? So what is the probability that person is tested positive given that the person has actually the disease, and this is what, 95% effective. 95 divided by 100. Probability of D complement, how, what is the probability of healthy persons? 9.5% by 100 you can say. Multiply by probability of E given the healthy person. So what is the probability for the test result is positive given that the person is healthy? 0.01. Is positive in this probability. So this is 0.0 means 1% you can say. So this is 1%. 1%. Now you have everything. What you can do? Now you can just compute the probability for D given E. So probability for D given E, how you can compute probability of D times probability of E. Probability of D is what? 0.5 divided by 100 multiply by probability of E given D. So this is the 95 divided by 100. Okay. Now this total is divided by what? 0.5 multiply by 95 divided by 100 plus 0.5 divided by 100. Are you getting this thing? So 5 multiplied by 95, this divided by 0.5 multiplied by 95 plus this answer. Now decimal point, this if you remove, then divided by 10, here also 10 and 10. So you can remove this. If you can take 5 as common, so 5 you can cancel, and 5 from here you can cancel, and what is here? 199. Are you getting this thing? You can take 5 common from here in here. So 5 is here cancelled, 95 remains, divided by, here you have the 95 plus 199. If you add this, then what is the answer? So this is the 294, and this is actually the answer. What is the, you can divide, and what is the answer? This one. So this is the answer. If the test result is positive, means test result is positive. If you are somebody gives that okay test result is positive, then what is the probability that the person is having actually disease? So see the situation here. See the impact. The probability that person is having disease 0.3231 and test result is positive. See the situation. So this affect if you are developing some system. This says that once you are going to develop some system, then accuracy is very important. Are you getting me? So accuracy is much important. Even it is, you may think that okay, it is only 1%, 1% false positive. So you have only just 1% false positive, and you may think that okay, it doesn't matter anything. But see the situation. If the population, we are dealing with the large amount of population, we have the big size of population, and even 0.01 or 1% false positive can create the problem. So the if person is tested and he has doubts, even it is not the 0.5%. So person has having disease, given that the test result is positive, the probability comes is 0.3231. This is amazing. So if person is tested positive, your test results comes and it says that okay positive, and say this is how dangerous it is. COVID or something like this, and you are testing and you believe that the test results is positive, and test result is positive, we believe that okay this is the 100%. Actually, if there is a error in the system, then see the situations like this. So if your system is not accurate, this says that once you are going to do the research, then you have to worry about the accuracy. Even if you say that okay 95% effective, 95% only, and only 1% is false positive. This can affect a lot if you are if you are dealing with some sensitive area. So this is a very medical line is very sensitive area. You know that prediction of the disease is a very sensitive area. If somebody is not having cancer and you are saying that okay, person is having cancer, and your test result for the cancer is positive, and that actually the probability for being cancer is 0.03, sorry 0.3231. This is the probability. And see that if layman person is not knowing that what is the probability, and you say that okay you have the cancer, your test result is positive and you have the cancer, and see the situation, the person's mentality. So mental status and everything persons can affect. So that's why whenever you are going to develop some system, even you are going for the prediction means a classification or anything, clustering or any finding the machine's accuracy. So we have to ensure that our machine should be as accurate as possible. Even a small amount of error can create a lot of problems. So this is one of the examples you have seen. So only 1% false positive results can create the situation like this. You are happy that okay 95% effective. So you are happy. Yes, 95% are effective. But see, even 1% false positive can create this kind of situation. So always, once you are going to do the research, you must be careful. Your system should be. That's why in the research work, people are telling that research is the study which should be the rigorous study, and you have to carefully observe the data. Your experiment must be careful. So this this is just one example which says that okay yes even 95% is effective, but if it is creating only 1% false positive, then the whole population, if you consider the probability, then actual probability is like this.